Today we are going to start by thinking a little bit about the unit we just finished and then going into our new unit. So to think about the unit we just finished a unit on polynomials. So the question I am going to ask is, can someone just give me a polynomial off the top of their head? Any polynomial will do. Any polynomial. Yes. All right, 3x plus 2. That's a good polynomial. Who can give me another example of a polynomial? Yes. Go. Right. That is another polynomial there. Right? So, polynomials, if I wrote y is equal to the square root of x, is that a polynomial? If I rewrote this as x to some power, that would be x to the 1/2 power. Can we have a 1/2 power for a polynomial? We cannot. It has to be an integer polynomial, meaning it has to be a whole number polynomial. So this right here is not a polynomial, but these two are indeed polynomials. And the unit that we are going to be starting today is on rational functions. You may have covered them a little bit last year or in previous years, but basically what a rational function is it's just any kind of fraction where on the top of the fraction you have some polynomial. So let's use our first polynomial here. So on the top of your fraction, in your numerator, you have a polynomial, and in your denominator, you also have a polynomial. So if we just use the two polynomials that were shouted out as examples, and we just put one over the other, that is a rational function there. Right? Basically just as long as your numerator is a polynomial and your denominator is a polynomial, you have one central term, just one fraction, and that'll create a rational function for you. Question is, y equals 1, is that a polynomial? If you have 1, can 1 be a polynomial? It can. So if I just had 3x plus 2, can that be a rational function? Well, if you say, well, no, because it's not over anything. Isn't 3x plus 2 just the same thing as 3x over 1? And since 3x plus 2 and 1 are both polynomials, that does count as a rational function. So any polynomial that you can think of is a rational function. And if you take a polynomial and you divide it by a polynomial, that is also a rational function. Right? So to look at rational functions a little bit more in depth, I would like to point our attention to, for you guys, it'll be this second problem here. Starts with g of x. And the problem with this problem is right now, if you look at this, is this one central fraction that has a polynomial on the top and on the bottom? No, because it's got this 2, right? And this is, because there's like a 2 and it's minus 3 over x plus 1, this isn't one central or one main fraction. So what that means is, in order to make this into a rational function, we need to rearrange this so that this is all just one fraction. Take a few moments, see if you can manipulate this in some way so that you can get this all as just one fraction. The polynomial on top and the polynomial in your denominator. Then I will pause while I give you a few moments to do so. Dice of Destiny gives us row 4, person 5. Yes. So, could you tell us the first thing that you did? Right. If we have a term and we need to subtract it by another term, and one of them has a denominator that's x plus 1, what do we need to have as a denominator in our first term? Does it need to be the same? Yes, it should be the same. So if I said person, or row 4, person 4 now, if we want this 2 to have the same denominator as this 3 over x plus 1, what should we do to this 2? So we're going to multiply the top and the bottom by x plus 1, and you're saying that 2 is the same thing as saying 2 over 1. And once we do this, this becomes our equation. And have we changed anything in our equation? Not really, right? We just multiplied it by the same thing on the top and the bottom, so it's okay. All right, would you like to call on somebody else? Okay? Yes, so what would you do next? All right, so taking out our denominators. So if we have the same denominator here and the same denominator here, what can we do with our two terms? Yep, so our denominator stays the same, and since it's the same denominator, we can just combine them. All right, would you like to call on somebody else? Okay. Looking at row 2, person 4, can you tell us what your next step would be? All right, so what do you end up getting? Which is, you said, minus 1 over x plus 1. So now we have rewritten our function, and this is indeed a rational function. Right? All right. Let's do one more of these. Let's do number 4. This one right here. This one's a little tricky because you have a fraction and it's divided by a fraction. If you're dividing by a fraction, what should you do? Should flip it first, right? If you're dividing by a fraction like you are here, you don't want to really divide, so you're going to flip it, and then you're going to change this to a multiplication. So I'm doing that. See if you can simplify this into just a single fraction. I will pause while you do so. All right. So, looking at number 4 here, if we know that we're going to switch, or I guess from our first step that we were talking about before, where we said, okay, we're going to take the top and the bottom and we're going to switch them, and then we can change this division sign to a multiplication sign. From here, row 2, person 1, can you tell me what you did next? Right. Can you tell me what you did next? Yep, after flipping them. Okay, so if you multiply them together, did you just keep them separate? So you said we just multiplied them. Did you multiply them across like this, or did you multiply them across numerator and numerator? All right, so we multiply across. So if we're multiplying across, we end up with 2x squared minus 1 times 3x minus 2 over, oh, I already made a mistake, didn't I? I forgot to flip them. So, trying this again, we have 2x squared minus 1 times x squared minus 1. And that is over x squared minus 1 times 3x minus 2. Ryan, can you call on somebody to tell us what they did next? Yeah, so if we look right here, we have an x squared minus 1 in our numerator and in our denominator. So can't we just cancel them out because it's the same thing? So we just cancel them out and we write what we have left. We just end up with 2x squared minus 1 over 3x minus 2. All right, so if that was everything that you needed to know about rational functions, this would not be a unit. Another thing that we need to know about rational functions are asymptotes. Who remembers asymptotes from way back when you guys covered those? If you look at the comics that I wrote, I don't know if you guys were able to look at these comics at the beginning, but who here has watched Lord of the Rings? You know, Gandalf, and how he like stands there and he's like, "You shall not pass." I just completely butchered that line, I'm sorry. But you can apply that to asymptotes. Asymptotes are basically, if you have an asymptote, then your graph cannot cross that line, right? So it'll approach the line. So if you see here on this graph, it'll approach the line, but it'll never actually cross it. And the same thing for down here, right? So if we are looking at, I'm just going to keep on this comic page because I like it. If we are looking here, we have this asymptote right here, which is this dotted line. And that's a vertical asymptote because it's vertical. If we have a vertical asymptote, what does that really mean for us? Well, what it really means is if we have a graph and our graph is approaching some vertical asymptote, let's look at what the graph's behavior is. So if I looked at the graph's behavior right there and I said, I want to write this in limit notation. Remember limit notation that we've been doing for the past week? If I wanted to write this in limit notation, we're going to start with the limit of f of x. And then we have to figure out what x is approaching and what our y value will be. So if we're looking at this, let's say that this is at x equals 1. Right? We have an asymptote at x equals 1. That means for our limit, as our x value in our limit approaches 1, because our asymptote is at 1, then what's going to happen to our graph? Turn and talk with your table partner, these two rows, these two rows, and these two rows. Turn and talk with your partner. What is our limit going to reach? Or I'll pause while we do this. Right. Is there somebody here who thinks they know? What is the y value going to reach as x approaches 1? This group over here was having a good discussion. Does somebody here want to share what they were talking about?
Well, we were saying as it approaches 1, it's going from right to left, so it's going to infinity.
Right. So we're saying negative infinity. So that is a very important point, and we were going to segue into that, but you have read my mind. So if we look at this part of the graph, as this part here is approaching 1, right? Up here, what is our y value? If it's pointing straight up into the air, it's going to reach infinity at some point, right? So it's going to reach infinity, but the point that was just brought up is, but that's if you were coming in from this direction. What if you were coming in from this direction over here? Then your graph is this red graph down here, and what is that approaching? Negative infinity. So if we're approaching 1, how can we both be approaching infinity and negative infinity at the same time? So there are two small things that we have to add to our idea of limit that we have not talked about yet. And those two things are, if we are looking at our limit of our function as x approaches 1, if we just want this part here as x approaches 1 from this side, it is approaching from the left side. If it is approaching from the left side, then we have to put a small minus sign above the 1, because this tells us that as we are approaching x, we are going to approach, this is as our x value is going to approach 1 from the left side. And if it approaches 1 from the left side, then our y value will go up to infinity. But is infinity an actual number? Like, can you count and get to infinity? You can't. So could you ever actually equal infinity? No. So something that we said before, last week, when we were talking about this, is we just said, oh, it just equals infinity. But that's not quite true, because you can't equal infinity ever. So what this does instead is this goes to infinity. So instead of putting an equal sign, you kind of have an equal sign, and then you put an arrowhead. Right. If we looked at this then, and we said, okay, we know that from the left-hand side, it will equal infinity. If we look at instead the limit of our function as x approaches 1 from the right-hand side, I'll write out plus for the right-hand side, then as we said before, that'll just mean that right here, our y value will go towards negative infinity. So we'll have our equal sign with our arrowhead, and so it goes towards a negative infinity, right? I will pause for a second. Continuing on from here, we have this limit notation. And so going back to this idea of vertical asymptotes, basically what a vertical asymptote will tell you is that at some value, if you have a limit where your function tends towards either infinity or negative infinity when you approach it from these sides, then there's a good bet, you have a good bet there, and it is almost ensured that you will have a vertical asymptote at that spot, right? So that's kind of how, looking at a graph, we can determine there is a vertical asymptote. If we were looking just at a function, let's jump a little bit. If we were looking just at a function, and we wanted to know from that function, how would we find the vertical asymptote? If you think back to the graph that we had, we said, okay, for that graph, our limit approached infinity, which basically meant that at the point itself, at x equals 1 for our example, our value for our function didn't exist. So if we look at this first example here, and we said, okay, if we know that the vertical asymptote will happen when my function doesn't exist, when will my function not exist for this first problem here? Well, let's look at this. We have a fraction. If you have a fraction, when does a fraction not exist? Can you divide a fraction by 0? Can you say 1 divided by 0? You cannot. So, if I just said, let's look at the bottom here. When does this bottom equal 0? And we just solve for the x values. At those x values is when our function will have some kind of vertical asymptote. So, if we just look at this here, that means x squared minus 3 is equal to 0. And if we solve this out, that is when x is equal to positive and negative square root of 3. So that means that we have two vertical asymptotes for this problem. And they are at x equals positive and negative square root of 3. All right. Try to find the vertical asymptote for this problem. This next one right here. Right? I will give you a few moments to do so. Figure out what the vertical asymptote is here. So, now that we have had time to figure out what our vertical asymptote is, would the person in the 5th row, person 1, could you please tell us what you got for the vertical asymptote here? Positive and negative 3? I don't know why I put a parenthesis there, but x is equal to positive and negative 3. All right. So, something else that we need to go over next is, on this page you'll see it says holes. We'll come back to holes. Let's do horizontal asymptotes first. All right. So, I think that's a good linear regression there. So, with horizontal asymptotes, question, yes. So we will come back to that. Yes, and that has to do with holes, but we will come back to it. So we're going to look at horizontal asymptotes first, because going from vertical to horizontal makes more sense in my mind. So for horizontal asymptotes, there are 3 different cases. And the cases depend on the degree of the polynomial in the numerator and the degree of the polynomial in the denominator, right? So if we have 3 different cases, case 1, let's give an example of case 1. Let's say we have our function here is equal to 3x minus 2 over 3x squared plus 4, right? In this case, if we look at the degree of our polynomial in the numerator and the degree of our polynomial in the denominator, what is the degree of the numerator? It's just 1, right? This is like an implicit 1. So our degree in the numerator is 1. Our degree in the denominator is 2. And so here we have the degree of our numerator is less than the degree of our denominator. If that is true, then your horizontal asymptote will be at y equals 0. Oh. If you have the degree of your numerator less than the degree of your denominator, then your horizontal asymptote will be at y equals 0. If instead we had a function that was 5x plus 2 over 10x minus 3, what do you notice about the degree of these two polynomials? This is 1, and this is 1, so they are equal. So if the degree of your numerator is equal to the degree of your denominator, then the horizontal asymptote that you have there will be a ratio. And you can find that ratio by looking at the coefficient of your numerator and dividing it by the coefficient of your denominator. And the coefficient that I'm referring to is the coefficient of your leading term. So, since right here, this is my leading term, 5x, I want to look at the coefficient of 5x, which is just 5. And then if I look here in the bottom at 10x, my leading coefficient is just the 10. And so that means that my ratio will be 5 over 10, which is the same thing as 1/2. So I will have a horizontal asymptote at y equals 1/2. You know what I just realized here? It's horizontal asymptote. Which way is your line going? This way, right? If you have a vertical asymptote, which way is your line going? This way. So if we looked back at our vertical asymptotes here, notice that we're saying x equals. Right here is an x equals. And notice here, we are saying y equals. That is a number 1 mistake that people usually mix up, is that they'll say, oh, my horizontal asymptote, x equals 0. If you think about it, x equals 0, that is not a horizontal asymptote, that is a vertical asymptote. So make sure you are getting your x equals and your y equals to correspond with the proper vertical or horizontal asymptotes. Okay, one more case. If I have the case where, let's say I have x cubed minus 3, and I have x plus 4. And I look at that, and I look at the degrees of my 2 polynomials here. The degree of my polynomial up here is 3, and this is 1. So that means that the degree of my numerator is greater than the degree of my denominator. And if this is true, then the horizontal asymptote that I will have is just none. I won't have one. based off of this, take the next few moments and look at these next 3 problems on this slide. If you look at each of these will fall under one of our cases that we just covered. And try and figure out the horizontal asymptote for each of these 3 cases. Right? So pause and give you some time. Now that we've had some time, row 4, person 4. Today's your lucky day. Can you tell us, pick one of these and tell us what your horizontal asymptote would be? Y equals 0. And can you explain your reasoning for why? Yep, so here our numerator is less than our denominator, so y has to equal 0. Awesome. Would you like to pick on somebody? Or, okay?
Second one is there's no horizontal asymptote.
All right, and then can you explain why you think that? So here our numerator is greater than our denominator in terms of degrees, so we have no horizontal asymptote. All right, would you like to pick on someone to give us the third one? All right, can you explain how you got there? Okay, can you ask your neighbor to help explain it to you?
Yeah, so I got -3.
Yes.
So I took the leading or the leading coefficient.
Yes.
Exactly.
Okay, so you took the leading term there.
On the bottom.
All right, so then we have our leading term on the bottom.
So then you have to divide 6 by 2.
All right, so the power of our numerator is equal to the power of our denominator. So that means that we have y is equal to the leading coefficients on the top and the leading coefficients in the bottom. And Olivier got -3. Awesome. Great. Now we can go back to holes. So show of hands, who has heard of a hole before, sometime in a math class? In a math setting, not just in a daily life setting. All right, show of hands, who remembers how to find holes? I have a confession, I did not know as of yesterday, so I had to remind myself. So holes are something where it's like you learn about it and then it just kind of goes away and you never really think about it anymore. But if we want to look at holes, if we look at this second problem that we had done earlier, so we're going to go back to this slide and we're going to look at this problem again. Okay? I'll give you 3 seconds to get there. Okay? If I look at the numerator, is that numerator factorable? Well, if you can factor it, you should. So if we looked at the numerator here and we factored it, what would we get? So, row 3, person 5. So, easy. Could you tell us what 2 factors you would get out of this? Right, so we get an x minus 3 and an x plus 2. Yeah, so if we look at the bottom, you can also factor out the bottom there. And you get x plus 3 and x minus 3. But if we look at this fraction that we now have, I see some repeated terms. So don't we have an x minus 3 on the top and on the bottom? So if we have one on the top and the bottom, can't we just cancel those out like we did before at the beginning? So once we have that, what we're left with is just x plus 2 over x plus 3. So this that we just canceled out, that is your whole. Okay? So whatever we have canceled out means if you can cancel it out, that means that you have a whole. And so what that means is that at x equals positive 3, because this was at x for x minus 3, at x equals positive 3, we have a whole. So then we have to go back here to our vertical asymptote from earlier. And looking at after we have canceled everything out, what we have remaining is just an x plus 2 over an x plus 3. So since that's all we have remaining, then that means we don't have plus and minus 3 as a vertical asymptote. Right? That means that all we have left is just this x plus 3 here, and if we set x plus 3 equal to 0, all we have is just x equals negative 3 is our true vertical asymptote. So because we can cancel out this x minus 3 here, there's a hole, which means that if there's a hole there, then there's not a vertical asymptote. But there is still a vertical asymptote at x equals negative 3. Right. Let's just do one problem where we find all the asymptotes and all the holes. Right? So if we look at this problem here, we want to figure out what the horizontal asymptote is. We want to figure out what the vertical asymptote is. And we would like to find if there are any holes. So take a few moments, figure out those 3 things, and I will pause the video while we figure those out. So if I can row 4, person 2, so that would be Bobby.
So for the horizontal asymptote, I got 1.
Right, and then how did you get 1 for a horizontal asymptote?
Because both the numerator and denominator have a degree of 2.
Okay, so the degree is the same, and your coefficients are 1 and 1. So is it y equals 1 or is it x equals 1?
Y.
Okay, y equals 1. If it's horizontal, flat line. Awesome. Would you like to call on somebody?
No, you can roll.
Okay. Rolling the dice. Row 2, person 5. Can you tell us either the vertical asymptote or the hole?
Okay, the hole is at x equals minus 2.
At x equals negative 2, can you tell me how you got there for the hole?
So I factored out the top or bottom,
Okay, so you factored out the top here and got x minus 3 and x plus 2. And on the bottom you got x plus 2 and x plus 2. Alright, and then you said you were able to cancel out an x plus 2. So you just said that the hole is at x equals negative 2. Alright, one thing that we haven't really talked about though, if you have a hole, should a hole be a line? Would it be x equals negative 2? No, it would be at some point, right? So if we know that it's at negative 2, that means that our hole would be at negative 2. And then how would you find the y value? Would you just have to plug it back in to our equation to get our y value? So we do not necessarily have to do that now, but we know that if we wanted to find the y value, you would plug in negative 2 back into our function and find what that y value is. Alright? Yes. It would not exist for...
The hole wouldn't exist.
Let's try it out. So on the bottom, if you put in negative 2 quantity squared plus 4 times negative 2, you would indeed... Yes, in the original one. You would end up with... You still would get 0, wouldn't you? On the bottom.
Yeah.
So, let me look into that a little bit more. But that is true for this problem. I think it could be a special case here. In fact, I think it is a special case, because if you look at your vertical asymptote, can someone tell me what the vertical asymptote they found was? X is equal to negative 2. So, Problem here is now our hole and our vertical asymptote are the same thing, right? So if they're the same thing, then that means that we do have a vertical asymptote at -2. And it just so happens that there is a hole there. But what is most important to us is that there is a vertical asymptote at that, on that line, right? Okay, because we are running out of time here, just to quickly look over this whole business and clarify, because we have a vertical asymptote here at x equals -2, that means that even if we did try to find the y variable here and plug it back into our equation, you would get does not exist, because there's also a vertical asymptote there. So of course it won't exist, right? So for this, that is all that we are learning about today. So if you would like to pull out the homework, I believe I have the homework on a different document. But if you would like to pull it out, I will tell you which ones you can skip. Let's see. It's not. Do I have it on this document? Oh, I do have it on this document. Never mind. All right. So if you look on this homework here, I would like you to do 1 and 3. Skip 5. And I would like you on this second page to skip 7, but do 8 and 9. And then on this third and final page, I would like you to try this one as well. But then you do not have to do anything after that. Yes.
What was the last page again?
Yes. So this is the first page, just the first 2 on the first page. On the second page, the last 2. And on the third page, just the 1. And that's it. And because I think you guys are confident on this material, I would definitely do the homework for tonight. Definitely. Okay. All right, so that is all we are going to be doing today.